Good day, grade 12s. I'm Mr. Masunda. I'm going to be teaching you guys mathematics today. And our topic for the day is application of calculus. You guys are already familiar with calculus. You should by now be able to use differential rules to differentiate functions. You should be able to plot the cubic function. And in some aspects of plotting the cubic function required you to use some calculus. All right, so now let us go through the outcome of today's lesson. So in this topic, we are going to apply the derivative of a function to solve optimization problems. At a later stage, we'll look at what optimization means, and then we'll also apply the derivative of a function to determine the rate of change of various physical quantities. Now, here what we are going to be doing is we are going to interpret the derivative as a rate of change. Now, let us now look at what we mean by optimization. If you are asked to optimize an outcome, it means that you must look for the best possible outcome. So if we say you need to optimize a function or optimize an output, we are looking for the best possible outcome. Now, let us look at an example. Take, for instance, you have a company that produces lunchbox. What do you think will be some of the best possible outcomes for this company? This would be to produce lunchboxes with a maximum volume. Now, this company will also like to produce lunchboxes using the least amount of plastic. So if you are using the least amount of plastic, it means that you are keeping the surface area to a minimum. Also, this company would like to produce lunchboxes that will keep the cost incurred at a minimum. Now, if you are using the least amount of plastic, then you can be able to accomplish your goal of keeping the cost incurred at a minimum. Now, also, ultimately, this company, like any other company out there, would like to produce lunch boxes that will generate maximum profit. All right. So now, if you seek the best possible outcome, it could mean one of the following things. It could mean minimization, meaning the smallest possible outcome. Now, if we look at the example that we looked at earlier about lunch boxes, minimization would mean keeping the surface area at a maximum. Now, looking for the best possible outcome could also mean maximization. And if we go back to the example that we looked at earlier, maximization would refer to maximizing the profit that this company is able to generate. Now, physical quantities which can be minimized or maximized are but not limited to the following. You can minimize or maximize areas and surface areas, volumes, velocity, acceleration. You can also minimize or maximize length. You can also be asked to minimize or maximize distance. Now, let us look at minima and maxima problems. So if you are getting a problem in a question paper and this question paper deals with minimum and maxima, what are the things that you are supposed to do? One, in all minima and maxima problems, you are going to be given a function, or you have to formulate your own function. Why do we do that? This is because if we want to optimize a quantity, we need a functional representation of that quantity. Now, let's say, for instance, we have a quantity of area. We are looking at area of something. Let's say, for instance, we have a box like that, and we are given the dimensions of that box as the length be negative x plus 4, and you have the breadth being x. So the quantity in question here is the area of that box that we are having there. Now, if we want to optimize this area, we'll have to have a functional representation of this particular area. And how would we get a functional representation of that? We'll say the area, it's equal to, so that looks like a rectangle. So we can say the area is given by length times breadth. So this will mean that we'll have negative x plus 4 times x. So we can remove the bracket, we'll have negative x squared plus 4x. So what have I done there? What I've actually done there is to give a functional representation of the area. So that is what you will be required to do when you are dealing with a minima or maxima question. Now, so it means that your quantity must be represented as a function. Say, for instance, in this example, my quantity is volume, so I'll have to have a functional representation of my volume as v of x equal to something, meaning that my volume will be a function of x. Now, once you are able to get a functional representation of this quantity, in order to find the minimum or maximum of this quantity, you are going to determine the derivative and set it out to 0. So now let us go back to the earlier example that I've given you guys. I said that our area as a function of x is given as negative x squared plus 4x. So it means that if I want to find the minimum or the maximum area of this, I'm going to say the first derivative of the area equal to, so you guys already know how to derive a function, so this becomes negative 2x plus 4. Now, I am saying the derivative must be equal to 0, so we are going to then equate that to 0. Now, once we have done that, once we have find your derivative and we have equated it to 0, you will then have to determine the value of a variable in order to optimize the function. So what does that mean? It now means that you are going to take the function that we have, you are going to take your function, you derive it, you equate it to 0. And then you are going to solve for the value of the variable that will give you a minimum or maximum quantity of the function that we are dealing with. So if we look here at the function that we have, the function of the area, we have successfully find the derivative and we equated it to 0. Now what we need to do is to find the value of the variable, which is x. That will make this quantity to be a minimum or maximum. So it means that x will be equal to 4 over 2, which is 2. So what does that tell me? It tells me that I'm going to have either a minimum or maximum quantity of the area at x equal to 4. All right, so that is what you will need to do to determine a variable in order to optimize your function. Now, once we have done that, I now know that the value of x, where you are either going to have a minimum or maximum, is equal to 2. But as it stands, I do not know whether my area is going to be a minimum or a maximum. So I can always check what my area is going to be at that particular value of x. And to do that, we are going to find the second derivative, and then you substitute the value of x where you expect to have this minimum or maximum on the second derivative. Now, if your second derivative is greater than 0, that means that you are going to have a minimum quantity. And if your second derivative is less than 0, it means that you have a maximum quantity. Now, if we can go back to the example that we are looking at here. So we found that we either have a minimum or maximum quantity for area at x equal to 2. So what then are we going to do? We are going to take the second derivative of this function. So we say second derivative of x, what do we get? We get negative 2. So it then tells me that the second derivative, it's what? It's less than 0. So what does it mean? It means that at x equal to 0, x equal to 2, I am going to have a maximum area. So that is basically what you do when you optimize a function. Now, in some questions, you can be asked to calculate the actual minimum or maximum value. Now, how do you then do that? What you are going to do is you are going to substitute the value of the variable where you have either a minimum or a maximum into the original expression. And then you solve it, you will get the actual maximum or minimum value. Now, if we can go back to the example that we were looking at, we've said the function of the area was given as negative x squared plus 4x. And we found that we have a maximum area at x equal to 2. Now they are asking us to solve for this maximum area. So to get the maximum area, we'll then say a of 2. So you replace x with 2. With 2 there. So you're going to get negative 4 plus 8. So it will mean that our maximum area will be 4 squared units squared. Okay, so that is basically what you do when we are dealing with minima and maxima problems. Now let us quickly go through an example. So we are told that an open box with a rectangular base is to be constructed from a rectangular piece of card measuring 16 centimeters by 10 centimeters. A square is to be cut out from each corner and the sides folded up. Each side of the square is x centimeters. Now let us go through the information that we are given before we even start looking at what questions we are being asked. Now, we have to first do a model of what we are given. So we are told that we have a rectangular card there, and its dimensions are 16 by 10 centimeters. We are then told that to make this box, we should cut out squares at each corner. And the length of this square, we are told it's x, so that is x. And then that is x, that is going to be x, and so forth. All right, so now, it means this part is going to be cut out. So that part will be cut out, that part will be cut out. So now we are then going to fold this card around that. We'll fold it around that, we'll fold that up. So this is basically going to be folded up. So it then means that this part here is going to be our height, the height of our box. So it means that that is going to be x there. Okay, so then our box, if we can give a presentation of what our box looks like, we'll have a box that looks like that with a length. Now, let's go back to what our length is going to be. We've cut out x, we've cut out another x. So it means that we are no longer going to be using the whole 16 centimeters for our length. What are we going to use? We're going to use 16 minus this x minus that x, which is minus 2x. And then for our breadth, we cut out x there and x there, so it means that we must subtract 2x on the breadth. So it means that now the question that we are dealing with will have a height, which is x, will have the length, which is 16 minus 2x, and we're going to have a breadth that is 10 minus 2x. Now, that right there is a very important part of the question that we are going to be doing, being able to come up with a model of this question. Now, let us look at what we are asked to do. The first question, they want us to show that the volume of the box is given by v equal 4x cubed minus 52x squared plus 160x. All right? And then secondly, they will want us to find the size of the cut-out square so that the resulting box has the largest possible volume. So very important here, they want us to determine the value of x in 1.2. Okay, let's look at the solution. So I've already gone through that with you guys, so you know how I got that. All right, so the first question, they want us to show that the volume of the box is given by v equal 4x cubed minus 52x squared plus 160x. Now, if you look at the box, our box is a rectangular prism. So it means that we need to know the volume of a rectangular prism. In general, the volume of a rectangular prism is given by v equal length times breadth times the perpendicular height. So we have an expression of our length, which is 16 minus 2x. Our breadth, it's 10 minus 2x, and our perpendicular height is x. So we remove the bracket, and we find that our volume is 4x cubed minus 52x squared plus 160x, which is what we're asked to show. So that is basically what we have done. So what was very important in that question is that we needed to know that the figure that we are dealing with is a rectangular prism. And we needed to know the volume of a rectangular prism, which was length times breadth times the height. And the rest is history. Now let us go to question 1.2. We're asked to find the size of the cut-out square so that the resulting box has the largest possible volume. Largest possible volume simply means maximum. So they are looking for maximum volume. And whenever you see in a question the word maximum or the word minimum, you should always think one thing. First derivative of your expression equal to 0. So what we have now is the expression for the volume. So we know that our volume is 4x cubed minus 52x squared plus 160. So now they are asking for the largest possible volume. So we are going to say first derivative. So this is dv dx. So we differentiate that, we'll get 12x squared minus 104x plus 160. And then we equate that to 0. Now, once we have done that, we'll have ourselves a quadratic equation there. Now, you will see that in this quadratic equation, we have the highest common factor there, which is 4. So what we've divided every term there by 4, and we're having 3x squared minus 26x plus 40 equal to 0. And then we find the factors of that. So the factors that we have is 3x minus 20 and x minus 2. So we use the zero factor rule to find the values of x. So we find that x equal to 2 or x equal to 20 over 3, which is approximately 6.67. Now, I want us to look at something because we have two solutions. We have x equal 2 or x equal 20 out of 3. So now, which of these solutions is going to give us a maximum volume? So now you'll remember that the expression for volume is 4x cubed minus 52x squared plus 160x. So now, from your time drawing cubic functions, you'll agree with me that this expression there represents a cubic fraction. And your a there is positive. So it means that we have a cubic fraction like that one. So there is your maximum and there is your minimum. So we expect that we are going to have that as the value of x equal to 2, and you'll have this value there as x equal to 20 out of 3. So you can clearly see that you're going to have the maximum volume at x equal to 2. But that is not the only way in which you can tell which one will give you a maximum or a minima. Earlier on, I said to you guys that you can always use the second derivative to tell whether you have a maximum or minimum at that particular point. So what we are going to do is then we're going to take this expression and we derive it twice to get the second derivative. So the second derivative here, this will be 24x minus 104. Now, if you take the value of x, which is 2, and we substitute it into this expression, we'll clearly see that this will give us the negative value, meaning that at x equal to 2, the second derivative is going to be less than 0, which means that you have a maximum volume at x equal to 2. If you can go and substitute approximately 6.67 there, you are going to get a positive value, and that means you have a minimum, which corresponds to the other question that we looked at on the other side. Now, that is what you are supposed to do when you are dealing with questions that deals with minima and maxima. The first thing that you must do is to find an expression to represent your quantity. So you have a functional representation of your quantity. The second thing that you'll need to do is to find the derivative of that particular expression, and then you equate it to 0. You then solve for the value of the variable where you are either going to have a minimum or a maximum. Once you have done that, you will have a value of the variable which gives you a minimum or a maximum, but we are not sure as to whether that value will give you a minimum or a maximum. So what you are then going to do is to take the second derivative and you take the value of the variable where you expect to have a minimum or a maximum. You punch it into the expression of the second derivative. Now, if your second derivative is greater than 0, then we are talking about minimum quantity. But if your second derivative at that particular point where you expect to either have a minimum or a maximum, it's less than 0, then we are talking about maximum quantity. So that is what you need to know about maxima and minima problems. So later on, we'll look at some exercises that deals with maxima and minima. But for now, let us look at rates of change. Now, rates of change is the extent to which one quantity affects a change in another related quantity. So it means you change one quantity and you look by how does the change in this quantity affect a change in the other quantity. Now, the derivative, which is dy dx, or it can be f prime of x, or any other form of writing the derivative. This is the instantaneous rate of change of y with respect to x. So we are basically saying that the derivative can be represented or interpreted as the rate of change. Now, whenever you are dealing with problems where one variable is changing with respect to another, you will have to use differentiations. Okay, so these are the things that we need to take away from this particular slide, is the fact that the rate of change is a representation of the derivative. So whenever they speak of rate of change, you need to think the derivative. All right, so now let us look at an example. We are told that water is flowing into a tank at a rate of 5 liters per minute. So we have a rate there. So the water flows into the tank at a rate of 5 liters per minute, so meaning every minute there is 5 liters that is flowing into the tank. Now, at the same time, water is flowing out of the tank at the rate of k liters per minute. So when 5 liters of water enters into the tank per minute. At the very same time, there is K liters of water that is leaving the tank. So we do not know how many liters those are, it's just K. So this tells me that at a later stage, we might be asked to find out what that K is. But nonetheless, there is water coming in and there's also water leaving the tank. Now, the volume in liters of water in the tank at any given time in minutes is given by the formula V of t equal 100 minus 4t. So this is the volume, the expression that will give you the volume of the water that is in the tank. So at any given time, if you want to know the volume of the water in the tank, that is the expression that you would use. Now let us look at what the questions are. The first question, they want us to determine the initial volume of the water in the tank. So you must always remember, whenever they speak of initial, that speaks to time. T will be equal to 0 in this case. So we'll look at that later on. And then the second question, they say, write down two different expressions for the rate of change of the volume of the water in the tank. So they are referring to rate of change. Remember, rate of change is the derivative. So it means that in this question, we are somehow going to have to deal with the derivative of the function of volume. All right, now, the next question will be for us to determine the value of K, that is the rate at which water is flowing at the tank. I told you earlier on that we might later be asked to determine what K is. Now, let us quickly go through these questions. Now, the first question is, what is the volume of the water that is in the tank initially? So initially, we said that T equal to 0. So we're going to take the expression for the volume. So that is our expression, and in place of T, we are going to sub 0. So we'll have V of 0 equal 100 minus 4 into 0. So there you see in place of T, we have substituted 0, and we find that there are 100 liters in the tank initially. All right, so now let's go to the second question. They say, write down the two different expressions for the rate of change of the volume of water that is in the tank. Now, to deal with this question, I want us to look at what is going on. So let's say we have a tank like that. So we are saying that there is water that is coming in, and at the same time, there is water that is leaving. And we are told that there is 5 liters per minute that is flowing into the tank. At the same time, K liters per minute, it's flowing out of the tank. And we are given an expression for the volume, which is 100 minus 4t. Now, they want us to give expressions for the rate at which the volume of the water in the tank is going to be changing. They want us to give two expressions. Now, the first expression, we can get it from the fact that water is coming into the tank, at the same time, water is leaving the tank. All right? So it means we can talk of the rate of water into the tank minus the water out of the tank. If we look at the water inside the tank, we subtract the rate at which the water is leaving the tank. That will give us the rate of the volume of water that is in the tank. So if we look at the rate of water into the tank, we said that was 5, and the rate of water out of the tank, we said that was K. So that will be one of the expressions. Okay, so now let us see what our solutions are. So we are saying in minus out will give us 5 minus K liters per minute. That is one expression for the rate of change of the volume of water in the tank. But there is another one that we are yet to look at, and that is the derivative. Remember, we said the rate of change, we can interpret that as the derivative. So now, if we take our function for the volume, and then we find the derivative of that, you can clearly see that the first, if we take the derivative of this, we're going to get -4. So first derivative of V will give us -4 liters per minute. Liters per minute meaning that this is rate. Okay, so the two expressions that we got would be 5 minus k liters per minute. The other one will be -4 liters per minute. This -4 here tells us that the volume of the water that is in the tank will be decreasing by 4 liters every minute. That is what that negative sign is communicating to us. All right, so those are the two expressions for the rate of change of the volume of the water in the tank. So now let us look at the next question. In the next question, they want us to determine the value of K. Now we have two expressions for the value of K. One is 5 minus K liters per minute. The other one is -4 liters per minute. Now these two expressions both represent the rate at which the volume of the water is changing. So these two expressions are equal. So that is what is going to be important for us to solve this question. These two rates are exactly the same, they are equal. So to solve for the value of K, we are then going to say that 5 minus K is equal to -4. We solve for K, we find that K is 9 liters per minute. All right, so now if we can just speak to the 9 liters per minute that we got. So you can clearly see that there is more water that is leaving the tank per minute than the water that is entering the tank per minute, because we have 5 liters entering the tank per minute and we have 9 liters leaving the tank per minute. That is what explains why we saw earlier, looking at the rate of the volume of the water in the tank, to say that the volume of the water in the tank is decreasing by 4 liters per minute. That is because you are having 5 liters entering the tank, and at the same time there is 9 liters leaving the tank. So the volume will be decreasing every minute by 4 liters. All right, so now that is rates of change. Now I want us to look at another topic, that is calculus of motion. Now, calculus of motion is an extension of the rate of change section. So this is just an extension of the rate of change section. However, in this section, we are going to deal with the rate of change with regard to displacement, velocity, and acceleration. Now, these three terminologies are not new to some of you, particularly those who are doing physical sciences. You are familiar with those topics from physical sciences. You started doing them in grade 10. Now, let us look at what we mean by displacement. Now, displacement refers to the distance covered in a certain direction. So this is what we refer to as a vector quantity. It has both magnitude and direction. All right. Now, let us look at velocity. Velocity refers to the speed of an object in a specific direction. Again, you will see we are speaking of a magnitude and a direction. All right, so it means that velocity is a vector quantity as well. Now, this part here is very important. It is the rate of change. And remember, earlier on we said that the rate of change refers to the derivative. So it means that velocity is the derivative of displacement. Okay, so that is very important. The fact that velocity is the derivative of displacement. What does it mean? It means that if I am given an expression for displacement, if I take the derivative of that expression, that will give me an expression for velocity. That is very, very important to what we are going to be doing. All right, so we also look at acceleration. Acceleration is the rate of change. That phrase is coming back again, the rate of change of velocity, but we said rate of change is the derivative. So what that means is that acceleration is the derivative of velocity. Again, it means that if we have an expression for velocity, you can find the derivative of that expression that will give you an expression for acceleration. All right, so now let us look at velocity in a bit more detail for those of you who are not really familiar with the term velocity. Now, this one we've already spoken to. We said that this is the rate of change of displacement. Now, as a symbol from science grade 10, you will remember that velocity can be given as delta x over delta t, which is the change in displacement over the change in time. And this is what we referred to as the average velocity. Now, I want us to look at the instantaneous velocity. You guys will remember in grade 10, those who did sciences, that when we were dealing with graphs of motion and we are looking at constant acceleration and you plotted a displacement versus time graph, you had a graph like that. And we said that the gradient of this curve will give you, the velocity of the object. Now, if you wanted the instantaneous velocity, it means that the velocity at a particular point in time of this function, you will then have to draw a tangent. You'll have to draw a tangent to the curve. So a tangent will be a straight line that touches that curve at one point. And then we'll then say that the slope of this tangent, the change in x over the change in t, will give you the gradient at this particular point of contact. And that will refer to as the instantaneous velocity. All right, so but now, earlier on in earlier lessons, you guys were told that the derivative, so we are told that the derivative is what? It's equal to the gradient of a tangent. So if we are saying that the gradient of this tangent is equal to the velocity of this object, it means that velocity in this question here can be then expressed as dx dt, and this dx dt is the derivative. Okay, so that's basically what I have used to actually give this expression of the instantaneous velocity. Okay, so from this, it basically tells us that velocity is the derivative of displacement with respect to time t. So the derivative of displacement with respect to time t gives us the velocity. So it means that if I have an expression for the displacement, its derivative with respect to time will give me the velocity. Okay, so now this is also very important because in some questions they are not going to ask you to give the velocity of the object, but they will ask you to give the speed of the object. Do not be fazed by that. Speed simply refers to the magnitude of the instantaneous velocity, which is given by that. All right, so now you will see, once you are doing these questions, that the answer of the velocity will either have a plus or a minus sign. Now you need to know that that plus or minus sign speaks to the direction of motion. Okay, the plus or minus sign that you're going to see in your answer speaks to the direction of the motion. Now, when you are doing a science problem, normally you'll need to choose a positive direction. Say you are doing a question in a straight line. If you choose the positive direction as to the right, it means that if you do your calculations and your answer is negative, it basically means that the object will be moving to the left. So if you get a positive answer, it means that the object will be moving to the right. So that is basically what the sign in your answer speaks to. It speaks to the direction. Remember I said earlier that velocity is a vector, it is a magnitude and direction. All right, now let's quickly go through acceleration. Now we said acceleration is the rate of change of velocity. Now in symbol, acceleration, it's given as delta V over delta t. So this is the change in the velocity over the change in time. And this is what in science we refer to as the average acceleration. Now, if we did something similar to what I did when I was explaining the velocity, we'll clearly see that if we want to get the velocity from a curve, the gradient of the velocity of what we call a velocity time graph will give us a acceleration. And we said that the gradient to a curve is the derivative, and that is the derivative that we are having there. All right, so it means that another expression for acceleration will be dv dt. Okay, and we refer to this as the instantaneous acceleration. Okay, so once we have an understanding of that, we can then say that acceleration is the derivative of velocity v with respect to time t. So meaning that if I have an expression of velocity, I can derive that expression and it will, with respect to time, and it will give me an expression of acceleration. Again, the sign in your answer simply refers to the direction of the acceleration. All right, so this is what I want you to take away from the few slides that we went through. One is the fact that velocity refers to the derivative of displacement. So it means that if you have an expression for displacement, you can derive that expression and you will get the expression for velocity. Now, if we have an expression for velocity, you can derive that, and then that will give you an expression for acceleration. So in a question where you are given an expression for displacement, for instance, they can ask you questions about the velocity, they can ask you about the acceleration of that particular object, and so forth. All you need to know is that you need to derive. If you derive the expression for displacement, that will give you an expression for velocity. If you derive the expression for velocity, that will give you the expression for acceleration. Now let us look at an example. All right, so we are told that a particle moves along a straight line. The distance s in meters of the particle from a fixed point on the line at time t is given by that expression. So they've basically given us an expression of distance. So distance is given by that particular expression. Now the first question that they want us to do is to calculate the particle's initial velocity. Now you must remember velocity is the rate of change of distance. Okay, this is when we are only considering the magnitude of the displacement. So do not get confused by now me saying that velocity is the rate of change of distance. All right, so now it means that if I'm interested in the initial velocity there, I need to first get an expression for velocity. And I'm not given an expression for velocity, I'm given an expression for distance. So if I can find the derivative of that, then I'll have an expression for velocity, and then I can be able to calculate the initial velocity of this particle. Now let us look at the second question before we go through the solutions. The second question, they say we need to determine the rate at which the velocity of the particle is changing. The rate at which velocity is changing. Okay, so this is, in other words, because we have rate there and then we have change in there. So this basically means that we need to look for the derivative of velocity. Now, what is the derivative of velocity? The derivative of velocity is acceleration. So in other words, in this question, they are asking us to determine the acceleration of this particle at t seconds. Okay, so that's basically what we are asked to do in that question. All right, now the next question, 4.3, they say after how many seconds will the particle be closest to the fixed point? Closest, I can say they are referring to minimum. Okay, so closest can refer to a minimum, and later on I'll explain to you guys why I'm saying closest point to the fixed point will be the minimum. Now let us go through the solution. Now we are asked to calculate the particle's initial velocity. So we have an expression for this distance, which is s of t equal to t squared minus 18t plus 45. Now we need an expression for velocity so that we can be able to calculate the initial velocity. But we know that the derivative of distance will give us the velocity. So we are then going to take ds dt. So this will be equal to vt, which is the velocity. This is equal to 4t minus 18. So you just basically differentiate that. If you differentiate that, that becomes 4, and then 2 minus 1, so that becomes negative 18, that becomes 0. Okay, you'll remember that from differentiation rules. All right, so it means that we now have an expression for velocity, which is 4t minus 18. All right, so they are asking about initial velocity. Initial, you should know t equal to 0. So it means that in the expression of velocity that we are having here, our t should then be equal to 0. So we're going to replace t with 0, and then we find that our answer is negative 18 meters per second. Again, like I said, the answer in your answer, the sign rather, in your answer refers to the direction. So say, for instance, in this question, we had chosen to the right as positive. It will simply mean that initially this particle is going to move to the left with a speed of 18 meters per second. That's how you should interpret this solution. Okay, so that is basically what I've outlined there, that the sign means that if you choose to the right as positive, then the particle moves to the left at 18 meters per second. All right, so let us look at the next question. Now the next question, they want us to determine the rate at which the velocity of the particle is changing at t seconds. So earlier on I said, because they are talking about the rate at which velocity is changing, so it means that this question is a question on acceleration. They actually want us to determine the acceleration of this particle. Now, to determine the acceleration of the particle, we'll take the expression for the velocity. Okay, now acceleration is the derivative of velocity. So we find the derivative of this. We are going to get dv dt equal a of t equal to 4 meters per second squared. So you will realize that this function here, or this expression, is not a function of time. So since it's not a function of time, it means that we have constant acceleration. Okay, so it simply means that we have constant acceleration. So now I want us to also look at the sign of our acceleration. The sign of our acceleration is positive. And if we compare it to the sign of our velocity, you can clearly see that the signs are different. Now, what happens when the sign of the acceleration is different to the sign of the velocity? It simply means that this particle is going to slow down. If the signs were the same, if they were both positive or both negative, it will mean that the particle is speeding up. So now because the signs are different, it means that the signs are, the particle is slowing down. All right, so now let us look at the second, the last question. They ask us, how many seconds will the particle be closest to the fixed point? So now, since we have established the fact that the particle is slowing down, it might not get to the fixed point. So we need to know after how many seconds will the distance between the particle and the fixed point be a minimum. So this makes this part of the question a minima and maxima type of question, where we say the derivative should be equal to 0. All right, but what derivative are we talking about? We are talking about the derivative of the distance, because we are looking for the minimum distance between the particle and the fixed point. All right, so we take the expression for the displacement, we derive it. So if we take s prime of t, which is the same as ds dt, this will be equal to 4t minus 18. Because this is a minimum question, the derivative must be equal to 0. So we equate the derivative to 0, and then now we must solve for t. We take 18 to the other side, we divide by 4, we get t equal to 4.5 seconds. All right, so we can check if really this time it's where we are going to have the minimum distance by taking the second derivative. So if you take the second derivative, you derive that, we are going to get the second derivative equal to 4, which tells us that the second derivative is greater than 0 at that particular point. So it means that you have minimum. So therefore, we can say that the particle will be closest to the fixed point when t equal 4.5 seconds. So that right there is the calculus of motion. All right, so we've basically covered all the necessary concepts that you will need to deal with in application of calculus. So now I want us to look at some few exercises where we are going to apply these concepts that we've gone through. Okay, so let us look at exercise 1. Okay, so we have a cylinder there. So let us look at the statement. It says that a drinking glass in the shape of a cylinder must hold 200 milliliters of liquid when full. Now, very important, this is a drinking glass. So what does it tell us? It tells us that this cylinder is open at the top. Okay, this is open because if you are calculating the surface area of a cylinder that is open and closed, the formulas, or rather the equation of the surface area is going to be different, because now you do not have a surface there at that end because it's open. So that is very important to note that fact. All right, so we are told that this cylinder must hold 200 milliliters of liquid when full, so that is the volume of the cylinder. Now let us look at the questions. We are asked to show that the height of the glass h can be expressed as h equal 200 over pi r squared. We are also asked to show that the total surface area of the glass can be expressed as S of r equal pi r squared plus 400 over r. And then we also need to show that, hence determine that the value of r for which the total surface area of the glass is a minimum. So we need to know for which value of r, since our surface area is a function of r, we need to know for which value of r will the total surface area of the glass be a minimum. All right, so let us look at the solution to this question. So we have to show that the height of the glass H can be expressed as that. Now look at what we need to express H as. We are told that we should show that H is equal to 200 over pi r squared. Now if you look at this 200 is the volume of the cylinder. So it means that for somehow we must make use of the volume of a cylinder to get that expression. And that is what we are going to do. The volume of a cylinder, it's given by the area of the base times the perpendicular height. And our base is a circle, so the area of a circle is pi r squared times the height of our cylinder, which is h. So it means that the volume is given as pi r squared h. All right? So the volume was given to be 200, so we replace V with 200, and then we make H subject of the formula. We find that H is equal to 200 pi r squared. Okay, so that's what we were asked to show. Pretty simple. Let us quickly go to the next question. The next question, we need to show that the total surface area of the glass can be expressed as S of R equal pi r squared plus 400 over R. Now, the surface area of a cylinder that is open at the top will be pi r squared plus 2 pi r h. Now, we are going to replace our h with the expression that was given for h, which is 200 over pi r squared. And then if we simplify, you will see that that pi would cancel with a pi in the numerator there. That r would cancel with one of the r's there in the denominator. And then you multiply that 2 with the 200, you will get 400. So this gives us that the surface area is pi r squared plus 400 over r, which is exactly what we were asked to show. Okay, so now the last question under this exercise 1.3 says that hence determine the value of r for which the surface area of the glass is a minimum. So this is a minima or maxima question. So it means the expression of this, the derivation of the expression of the surface area equal to 0. That's what you need to remember. Whenever you are dealing with a minima or maxima problem, first derivative of the expression of what you are looking for equal to 0. Okay, so we take the expression for surface area, we derive it, we take the derivative of that, we get 2 pi r minus 400 over pi r squared. Okay, so you guys should know how to do that by means of just making use of differential rules. Okay, so because we have a fraction and I don't really like dealing with fractions, I'm going to multiply every term there by r squared. So then I'm going to get 2 pi r cubed minus 400 equal to 0. Now it then follows that r cubed is equal to 200 over pi. I'm just simplifying them, and then I get my r to be cube root of 200 over pi. Now I still need to verify that I'm going to have a minimum surface area for that value of r. Now to do that, I'm going to take the second derivative. Now if I take the second derivative of the expression for surface area, I find that the second derivative is 2 pi plus 800 over r cubed. So if you can substitute that value in there, you can clearly see that your second derivative is going to be positive. So what does that mean? It means that the second derivative at this value of r, it's going to be greater than 0. And we said earlier that if second derivative is greater than 0, that refers to minimum quantity. So therefore you can conclude that for total surface area r equal to cube root of 200 over pi, which is approximately 3.99 units. Okay. So I think that is all we have for today. I have some questions that I would like you guys to go through so that you can familiarize yourself with application of calculus. For one, this is the question that I want you guys to go through as well, whereby you are going to apply in calculus in a question that also entails functions. All right, so in this question, what's going to be important is to identify which type of question it is. Is it a rate of change question? Is it a minima or maxima question? Okay, so you can clearly see from the first question that we are having there that they speak of maxima. So it's a minima or maxima question, and they speak of the shaded area AOCB. Now, if you look at the shaded area, you should be able to identify what that shaded area is. And to me, that shaded area looks like a trapezium. So once you identify that that is a trapezium, you can then be able to recall what is the area of calculating a trapezium, which is half the sum of parallel lines times the perpendicular height. So clearly you will need to know the length of these parallel lines, and then you will also need to know the length of the perpendicular height, and then you can find the expression of this trapezium. All right, so the second question, they actually ask you to determine the maximum shaded area. So you can see that this shaded area is a function of area. So since this is a function of, it's a function of x. So since this is a function of x, so it means that we will need to then find the value of x where we have a maximum area, and then we take that value of x, we substitute it into the expression for the area, and that will then give us the maximum area that is going to be shaded. Now let us quickly go through the solution. So I said first, you identify the shaded area. So we've identified that shaded area as the trapezium. Now a trapezium, its area can be given as half the sum of parallel lines times the perpendicular height. So that is supposed to be a perpendicular sign there. So now, the things that we are supposed to do now is to work out the point B. Now this point B, it's given as bx is to y, but on the question we're told that y, which is ED, it's equal to negative 2x plus 10. So everywhere at this point, y is given by negative 2x plus 10. So it basically means that you can replace that y with negative 2x plus 10. Now on the statement, we're also told that BC is perpendicular to the x-axis, meaning that this is a vertical straight line, so which tells us that the value of x at this point is the same as the value of x at the point C. So that is why we are saying that the coordinates at C will be x is to 0. All right, so another thing that we need to do is to calculate the length AO. The length AO will be 8 minus 0. Since this is the origin, the coordinates there are 0 is to 0. So the length there will be 8 minus 0, which is 8 units. Okay, we also need to calculate the length BC. So the length BC, we're going to get that as negative 2x plus 10 minus 0, which is negative 2x plus 10. And then we need also our perpendicular height, which is CO, and that is going to be x minus 0, which is x. So it means that the area of a trapezium can be given as half the sum of the parallel lines, which is AO and BC. So it's going to be AO plus BC times the perpendicular height CO. We substitute the expressions for these distances into that. We'll have half into 8 plus minus 2x plus 10, all of that multiplied by x, and then we remove the bracket. We find that the area can be expressed as negative x squared plus 9x. You'll remember earlier on, we said that in a minima or maxima question, you are either going to be given the expression of the quantity in question, or you'll have to come up with an expression of the quantity in question. In this case, we had to come up with the expression for the quantity in question. Now, we have found that that expression of the area is given by negative x squared plus 9x. Now, but the question is on maximization of this area. So for maximum area, we need to say the first derivative equal to 0. So we derive the expression for area, we get negative 2x plus 9, we equate that to 0, and then we solve for x. And we find that x will be 9 over 2 or 4.5. All right, so we need to still verify whether at this value of x we are really going to have a maximum area. And to do that, we use the second derivative. Okay, we take the second derivative. We can clearly see that the second derivative is negative 2, so which means the second derivative at this point is going to be less than 0, and that will mean maximum area. So it means that the maximum area is when x equal to 4.5. Now, let's look at what the question wanted us to do. They wanted us to find the coordinates of B such that our area will be a maximum. And you will remember that our area, our point B, we said was x is to negative 2x plus 10. So we substitute x, so that will be 9 over 2, and we substitute x in place of, in the expression negative 2x plus 10, we are going to get 1. So it means that the coordinates of B will be 9 over 2 is to 1. Now, for the very last question of the day, they want us to determine the maximum shaded area, AOCB. So we're going to take the expression for the shaded area. The expression for the shaded area we said was negative x squared plus 9x. Now, we are going to replace x with a value of x that will give us maximum area. And that value of x we found to be 9 over 2. So we replace x with 9 over 2, and we find that our maximum area is going to be 20.25 units squared. All right, guys, that is all that I have for you today. So the advice that I can give you, just practice, 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 practice. You need to remember, whenever you are dealing with minima and maxima problems, the first derivative equal to 0, you find the variable, where you are either going to have a minimum or a maximum. Okay, to check whether you're going to have a minimum or maximum, you can always try the second derivative. So if the second derivative is less than 0, you will have a maximum. If the second derivative is greater than 0, you have a minimum. All right, so that is it from me. Until we meet again next time, goodbye.